Hey folks! Okay, so we are on to chapter 20, which is electrochemistry. Really important topic, helps us sort of understand lots of different processes, including how batteries work, fuel cells, and gives us sort of the foundation so that we can learn about those kinds of things. In order to do electrochemistry, we have to do a little bit of a review of redox chemistry, oxidation reduction, okay? Which we did back in chapter 4. So we're going to do a little bit of a review on that real quick, and then we're gonna take those concepts farther. In a oxidation reduction reaction, a redox reaction, there's an exchange of electrons, right? One reagent gives up electrons, okay? And if it gives up electrons, it becomes oxidized. And another reagent accepts electrons, and in the process of accepting electrons becomes reduced. And you might remember the one that gets oxidized, giving up the electrons, is called a reducing agent because it caused that other one to be reduced. And the one that accepts electrons, or you could almost think of takes electrons from the other one, and thus becomes reduced, is considered an oxidizing agent because that's the effect it had on that other compound. Yeah, okay, let me write some things on the board really quick. Okay, so chapter 20. Chemistry. Alright, so intro, oxidation, states, and oxidation reduction reactions. Okay. Alright, so oxidation reduction. Oxidation reduction reaction involves compound losing electrons and another gaining electrons. Okay. It's a fundamental process. Combustion, so when we burn things, that's an oxidation reaction. That's elemental oxygen acting as an oxidant on some fuel. So combustion, rust, batteries, etc. A lot of metals will corrode. Okay, so I don't know how many people have silver anymore, but if your family had like fancy silverware and stuff made out of real silver, you have to polish it because just sitting out in the oxygen in the air, you get a coating of silver oxide on it, which gives it that sort of dull look. Metals corrode from O2. Iron, copper, silver, etc. Okay. Oh yeah, an example. Statue of Liberty is made out of copper. Okay, and so you know it should have that sort of orangish reddish color that like copper wire does, but it's sitting out in oxygen for years and years and years, and so it's turned green, copper oxide color. Statue of Liberty is copper, but in air, the copper metal turns to copper 2+, specifically copper oxide. Okay. And as I said before, compound or an atom gains electrons it becomes more negative, okay, and is reduced. Okay. Compound or atom loses electrons, becomes more positive, and is oxidized. Okay. All right, so one task that you could have to do is you may need to look at a reaction and decide if, okay, here's a reaction, is this an oxidation, reduction, a redox reaction? And the easiest way to do that is to see if there was exchange of electrons somehow. If there was exchange of electrons between compounds or atoms, then it is indeed a redox reaction. And the easiest way to monitor that is to look at the oxidation states of the different atoms on each side of the reaction arrow. And if the oxidation state changed in something from reagents to products, then there was an oxidation reduction reaction. Okay. All right. They need to identify if a reaction is a redox reaction. Okay. Thus, check if exchange of electrons. Okay. You could count all the electrons in every atom. Compound, okay, and do it on both sides, and then see to the total number of electrons in this compound, or this atom would be a safer way to do it. Total number of electrons in all these atoms stayed same or change over here. Okay, But that's going to be a tedious way of doing it. But tedious. Okay, so oxidation numbers represent sort of a shortcut for figuring this out. Oxidation number and shortcut bookkeeping to do the same. Okay. Forward a little bit. All right, so I'm going to review a little bit on how we figure out oxidation numbers. Okay. A lot of the time, first of all, there's some rules of oxidation numbers. You'll remember things like oxidation, or the oxidation number of oxygen is always -2, except in peroxides, specifically for our purposes, hydrogen peroxide. Fluoride is always -1. If it's just a single atom ion all by itself, then the oxidation state number equals the charge number. Okay, so sodium plus, it has an oxidation number, oxidation state number of +1. Okay, and any element in its elemental form, so some metal that's just pure metal with the little zero sign above it, not so pure silver, pure gold, something like that. Those are all oxidation states of 0. Any other compound in its elemental state, so O2, that's how oxygen exists in its elemental state. Its oxidation state number is 0 as well, N2, things like that. Okay, I want to do, before we get into figuring out oxidation state numbers, just want to do a quick little review because we learned about oxidation state numbers way back when, and then we kind of marched on through all these chapters that we've been through, and we've looked at other sort of charges. Okay, we've looked at specifically we looked at formal charges, and that can get a little confusing. Wait a minute, how does oxidation state number and formal charge number, how do those compare to each other? How are those the same thing? And no, they're not exactly the same thing. So oxidation state numbers, in a sense, you could say, they look at a compound and they say there's no sharing of electrons whatsoever. Okay, usually the more electronegative atoms have all the have the majority of the electrons, and we're talking about valence electrons here. Both of them are assessments we do looking at the valence electrons because it's always simpler just to look at the valence electrons. In formal charge, you were looking at bonds, okay, and you're looking at how many electrons are near an atom. If you did that chapter with me, you know that I always talk about electrons that are near. So you look at a shared set of electrons, a bond, okay, and only 1/2 of the electrons of bonds count towards that atom's formal charge. Okay. Really, oxidation state number is just a really, we've set up some rules. It's sort of a bookkeeping technique to be able to identify if there's been an oxidation state change, a redox reaction. Okay, and formal charge is a way of looking at, we're not so worried about was there an exchange of electrons. We want to look at a compound and all its shared electrons and everything, and decide is there an atom in there that actually has a negative charge or a positive charge on it. Okay. Because that's an area on that molecule or polyatomic ion of sort of positive electron density, or I shouldn't say positive electron density, positive charge, okay? And that might dictate the reactivity of that compound. That atom of that compound that has positive charge might react with something that's negative. Okay? And then also, we also have partial charges, okay? So that's looking at if you have maybe you've got two atoms bonded, okay, and you've done the formal charge assessment, and nope, all the atoms in this compound are neutral, okay, and so if you might remember, by definition, that's a molecule, okay. However, we know that some of the ones that do the sharing, they don't share equally, okay. Oxygen doesn't share equally with hydrogen. It's more electronegative, so it steals some of the electron density. So there may not be a negative charge on oxygen, but there's a partial negative charge on oxygen because it's not equally sharing. Okay? So that's the difference between oxidation state numbers, formal charge numbers, and partial charge. All right, so let me put all that junk on the board real quick. Okay. Oops. Guess. Yeah. Shoot. Okay, I forgot my outline. I've messed up a little bit. Okay, this is. I apologize. Oxidation reduction was section I, and so section II is oxidation numbers versus formal charge. Okay, versus partial charge. Okay. All right. So, oxidation number. Give a little definition. Shortcut. Technique. Identify if redox happens. Okay. In this tool, we don't really take into account any shared electrons. Okay. Formal charge. Assesses number of electrons around an atom. Okay. In a compound. And compares to the protons in the core. Okay. You know, for instance, when I taught formal charge, I may not have made that point that you're comparing it to the number of protons in the core. Okay. I usually teach it that you're looking at the number of electrons, looking at shared bonds, and you're looking at the electrons that are near that atom. And I use a special definition near, half the bonds and all the lone pairs. And then you're comparing it to the number of electrons that are near in the periodic chart. Okay. If it's more, then it's a negative formal charge. If it's less, then it's a positive formal charge. Well, that's really just looking at looking at that periodic chart number of valence electrons, knowing that that thing's neutral, and so the number of electrons in that compound in the periodic chart, number of electrons equals the number of protons in the core, the number of protons in the core, and if there's one extra, then you've got one more than in the core, and it's negative. Just so you understand why I'm suddenly talking about the number of protons in the core. Okay. All right. And this helps identify charge, no charge. Oops. In each atom of a compound. Okay. Atoms only get 1/2 bonding electrons. And all lone pair, LP. Okay, just a reminder about that. All right. And then partial charges. Polarity, right, so if you have partial charges, that can also tell you what the polarity of a bond is, okay? Not all shared electrons are shared equally. And this takes into account electronegativity, En. Okay. And it's going to tell us if there are, again, maybe not full charges on a particular atom in a compound, but sort of charged areas. So partial negative, partial positive, things like that. Okay. All right. So that's just differentiating those three terms, in case that was confusing. Okay, so now I talked about the list of rules and stuff. The list of rules, list of rules for looking at oxidation numbers, okay? So oxygen is always -2 unless it's in hydrogen peroxide. Halogens, fluoride is always -1. The other halogens are usually -1 unless they happen to be in compounds that have oxygens around them, and then they're going to have a positive oxidation state number. Compounds that are in their elemental form have a 0 oxidation state number. Hydrogen, if it's bonded to a non-metal like oxygen or nitrogen and stuff like that, then it will have a +1 formal charge. If it's bonded to a metal, okay, like in a binary compound like sodium hydride, lithium hydride, so sodium H, things like that, then the hydrogen actually has a -1 oxidation state number. Okay, yes, that's about it. Oh gosh, I'm so sorry, folks. I think I've really messed up my my outline numbers here and stuff. So now, okay, well, you know what I'm just going to do. Another B there. Okay, so this should be Roman or section B. So sorry. List of rules. Section A was intro to oxidation state numbers. Okay. Section B is list of rules having to do with the oxidation state numbers. All right, so the first rule, as I mentioned, any atom in elemental form oxidation number is 0. Okay. So, examples. Carbon, solid, okay? Could be graphite, diamond, all kinds of carbon compounds. Nitrogen gas. Solid gold. Phosphorus. Exists in a tetramer. Okay. Oxidation number is 0. Okay. Rule number 1. Any monoatomic, so one atom, ion, okay, chloride, sodium, so forth and so on. The oxidation number equals the charge. Okay. Yeah, calcium always goes to +2. So the charge of an ionic calcium is +2, and the oxidation state number is +2. So sodium plus, that's an oxidation state number of +1. Oxide, okay, that's an oxidation state of 2. I guess, I don't, oh no, yeah, so oxide, sorry, not O2 minus. Oxide is an oxide is a -2 ion and a -2 oxidation state number. Calcium, as I mentioned, 2 plus, has an oxidation state number of +2. All right, okay, and then so non-metals, you know, on the periodic chart, things over sort of this area right here. Those tend to be negative, but again, kind of like the halogens, or I said for the halogens, they can be positive, particularly if they're in compounds with oxygen. Okay. All right. So, but in general, non-metals, okay, often negative oxidation number, but not always. Okay. Sorry, I'm going to clear my board real quick. And again, this might, or this is all review up to this point, but it's been a long time since we went over that, possibly an entire semester ago. And you need to know these pretty darn good to be able to do the next tasks that we're going to do in electrochemistry. Okay. Okay, so under oxidation, non-metals are often negative but not always, is the rule I said about red, the rule I said about oxygen. So oxidation number of oxygen is always -2, okay? Except in peroxides. Okay, in peroxides, the oxidation number is -1, right? in any polyatomic ion, the oxidation state numbers have to add up to the overall charge. So in peroxide, the overall charge is -2, but there's 2 oxygens, so each one has to have an oxidation state of -1. Okay? Again, for our purposes, it's really just going to be hydrogen peroxide that we have to worry about. Okay? Other than that, it's -2, and in figuring out sort of the oxidation numbers of a compound, that can often help us by starting out, okay, well, I know what the oxidation state of oxygen is, and then you sort of work your way, and by process of elimination, figure out maybe a harder atom to figure. Okay. B. If hydrogen bonded to a nonmetal, oxygen, nitrogen, sulfur, so forth and so on, okay. Then it's +1. Okay. So, for instance, H2O, that's hydrogen bonded to a nonmetal. So each of these are +1. We already know that that's -2. Or here, this is the way I usually do it. +1, each of them are +1, so a total of +2. Neutral, it works. Okay. All right, and then C. Oh, sorry. Nope. If, however, H is bonded to a metal, then the oxidation number equals -1. Okay, so say lithium hydride. Okay, this is -1. Lithium is in ionic form, it's always +1 cation, and its oxidation state number is +1. Okay. All right, C, halogens. Mentioned those. Okay. Fluoride. Unless it's in its elemental state, F2, okay, fluorine gas, right? If it's in any compound other than fluorine gas, it's always -1. Okay. Chlorine, bromine, and iodine are usually -1. But will be positive if, and they can be all different oxidation numbers, and those are sometimes the more challenging ones to figure out, but it's not that bad when we do the process of elimination approach. Okay, so, but will be positive if combined with oxygen. Some of these things can actually make a little bit of intuitive sense too. So the oxidation state number of hydrogen is a positive thing, +1, when it's with non-metals, because non-metals tend to be more electronegative. Okay, so that's why that rule is that way. The metals tend to be less electronegative than hydrogen. So in that situation, hydrogen, and according to the rules, gets the -1, and the metal gets the +1. Okay, and then it also agrees with the common charges of ionic compounds. Okay, and then oxygen is more electronegative. I think it's more electronegative than chlorine. It's real close to chlorine. It's definitely more electronegative than bromine. It's definitely more electronegative than iodine. Okay, and so it would make sense that if these are combined with oxygen, then these are going to take on a positive oxidation number. Let's see, am I done with rules? I'm done with rules. So let's actually figure out the oxidation numbers of some compounds. Okay, so like I was saying, sometimes when you're trying to figure out oxidation numbers, there might be, a few atoms in the compound, and one of them you're just like, I have no idea. That's really weird. But maybe the other atoms in the compound you have an idea about, and so you can figure what those oxidation numbers and their sum numbers should be, and then it should add up to the overall charge, and so you could sort of figure it by process of elimination. Okay, so we are in section 4. Oxidation numbers must add up to overall charge. Often an atom in compound, not sure of oxidation number, but can deduce from the other numbers. The other oxidation numbers. Okay. All right, so let's actually do some examples. Determine oxidation number in following compounds. Okay. So A, B, and what I would suggest is pause the video and then try to do these yourself before we go through and do them together. D. Sulfite. Okay. Okay, yeah, like, suggest you pause the video, try to do those, and then we'll go through and do them together. All right, so let's go through these. Okay, so on this first one, anytime you see oxygen, unless it's in hydrogen peroxide, that's kind of a nice place to start. So we know that each of these oxygens is going to be a -2 oxidation state number. And so what I tend to do on the air, -2 there, and so total is going to be -6, okay? It's an overall neutral compound, so you know that this all has to add up to +6, so each of the aluminums must be +3. Okay, so oxidation number of +3 for the aluminum. Fluorine here, that was one of our rules we learned. It's always -1. So -1, so -4 all over. So your xenon is +4. Okay. And here we have chromate. Okay. So again, your oxygens are going to be -2 each, so that's going to be -14. Potassium, in any ionic compound, potassium is always going to be +1 cation. Okay, it's in that first period, the alkali metals. Okay, so if the ion is +1, then the oxidation state is +1. Okay, so these are a total of +2. The overall thing is neutral, so the chromium here has to account for -12, and there's 2 of them, so each of them have to be -6. All right, this is hypochlorite. This is bleach. All right. You may know that this is a -1 anion. You were tasked with learning that back when we were doing naming of ionic compounds and stuff, but you may have forgotten it. And that's okay. You know that these, that's going to be -2, and there's 2 of them, so -4 there. Okay. Calcium always goes to +2. Okay, it's an alkali earth metal, so kind of like the same situation we had with potassium. All right, so these 2 chlorines, there's 2 of them, right, have to account for negative, what do you call it, negative, the right compound? Yes, I did. Oh no, I'm sorry. Have to counteract -2. So each of these chlorines must be +1. All right, for a total of +2. Now it's neutral. So the oxidation state of chlorine here is +1. Remember we said that the halogens are usually -1, except when they are in compounds with oxygen. Okay. This is sodium sulfite. Okay. You again may have learned that this polyatomic ion is a -2 anion, okay? But actually doesn't matter, you don't even need to remember that to do this. So -2 for each of the oxygens, so -6 total. Sodium is an alkali metal, just like potassium, so those are each +1, so +2 here. So the sulfur has to counter -4, and so the sulfur must be +4 because there's just 1 sulfur. Make sense? So that's the oxidation. So the oxidation number. Hopefully my little notation isn't messing anybody up. The aluminum here, the oxidation state number for aluminum is +3. That's just showing that the overall compound balances out to neutral. Okay. Oxidation state number here for chromium is -6. +1, +4 here, there's only 1 sulfur. Okay. All right. And then iron nitrate. So each one of these oxygens, and there's 3 of them, each one of those oxygens is going to be -2. Okay. And yeah, you could do it just for this compound here. Okay, so maybe that's going to be confusing way to say it. Yeah, so, well, yeah, I guess, let's see, you have to in this case. That's -6 for that guy. Huh. Yeah, I think for this one, actually, you really do, I'm blanking if there's a way to do it without remembering that nitrate is a -1 polyatomic ion. So you know that this ion has to add up to -1, okay? And so for it to add up to -1, the single nitrogen must be +5, okay? And then since this is -1, you know that the charge of the iron has to be +3, because there's 3 of these nitrates. Right? Okay. And it's +3 overall. And so the oxidation state of iron is +3 on that one. Okay. Okay, so now we're going to look at some reactions. The first one we're going to look at is metals in their elemental state. Okay, so a pure metal reacting with an acid. Okay, in that situation, the metal is going to get oxidized into a cation. Okay, it's going to give up electrons. What's going to accept those electrons is the proton of the acid, and kind of intuitively, hopefully, makes some sense that protons in an acid are very positive, so it makes sense that they would attract the electrons away from the metal. Okay, and the products that you get are you get the cation from your metal, and then you get hydrogen gas. And the counter ion for your new cation that you created is whatever the counter acid, the acid's counter ion was. So if it was hydrochloric acid, HCl, once that proton turned into hydrogen gas, that chloride is going to be the anion that goes around with the cation now. Okay. All right. So this is. Here. Oh boy. So sorry, I think this is C. I'm terribly sorry if that's incorrect. Okay, so oxidation of metals by acids. Okay. And we're also going to look at other salts that have a metal that can get reduced. Okay. All right, so we've said this a bunch of times, but if something gets reduced, something else had to be oxidized. Okay. Some definitions I want to remind you of. Okay, you know these, but so we have reducing agent. Okay. It gives the electrons to another compound. Okay. And in the process, the reducing agent gets oxidized. Okay, so within this section, the metals in their elemental state, the pure metal, is going to be our reducing agent. Okay, and then an oxidizing agent accepts or takes, however you want to say it, electrons from the reducing agent and in the process the oxidizing agent gets reduced. Okay. All right. There are many types of redox reactions. So here, the first one we're going to look at metals in elemental state. This is what I introduced, what we're going to talk about. producing acids. Okay. As I discussed, products are always going to be the same, or the same types. Okay. The metal is going to turn into a cation. Okay. And it is going to use the counter ion from the acid. So with counter ion acid. Okay. And then the other is, so the proton from the acid is going to turn into hydrogen gas. And board real quick. All right. Okay. Right, and I've got a note here. I won't put it on the board, but we already know that in general metals tend to give up electrons so that they can achieve the electron configuration of the nearest noble gas, and an oxidation reaction is one way in which they do that, or one context in which they do that. There are a few metals. Don't work well with acid. Copper is one. What's that one? Oh, and silver. Okay. All right. Okay, and then the second type I want to talk about is a metal in elemental form. Reducing another metal cation. Okay. You may remember we could look at, we looked in chapter 4, we looked at activity series, and we said that, well, if we want to know, will this metal reduce that metal, the reducing agent has to be higher on the activity series, otherwise it won't. And if it wasn't like that, none of these reactions would work, because you're going to create another metal in its elemental form, and if all the metals could react with all the cations, it would just go back. Okay. All right, so example of that real quick is, say, iron, solid iron, reacting with nickel nitrate. Okay. That's turning into iron nitrate. Plus nickel metal. Okay. And I might remember we can look at the net ionic. Okay. So the nitrates are not changing, so those are spectators. Oops. Sorry about that. Pen's dying. And our net ionic iron solid plus nickel 2 plus aqueous goes to iron 2 plus and nickel solid. Okay. And again, like I was saying, this isn't going to go backwards. The nickel isn't going to reduce the iron because nickel is below iron on the activity series. Okay. And it's not just due to the fact that it's on some chart. In a sense, nickel holds on to electrons better than iron does. Okay. So it's not going to give up its electrons to iron to make iron 2 plus to make iron metal. It goes, the reaction just stays that way. All right, so another thing that you might be tasked with is you might be given a full equation, and you might be asked to first identify was there a redox reaction, and if there was, what got reduced, okay? What was the oxidizing agent, or what got oxidized, in other words, what was the reducing agent, okay? All right, so, and the easiest way to do that is to just look at a compound and figure out all the oxidation numbers and see who changed and how did it change. If the oxidation number become more negative, then that compound was reduced. If the oxidation number became more positive, then that compound was oxidized. Okay. All right. Sorry. All right. Yeah, okay. I'm so sorry, my outline is just completely messed up. I'm just going to say stop. All right. Identifying oxidation and reducing agents, okay, of a reaction. All right. So our process determine oxidation numbers, all elements, see which were reduced or oxidized. Okay. I think it's clear, but I guess I'll just write it. Whichever, how do I say it? Whichever compound was oxidized, okay, that's the reducing agent, okay? And whichever compound was reduced, that's the oxidizing agent. Okay. All right, we'll do an example here in just a sec. And so, like in this example, there's a bunch of compounds, and so a bunch of oxidation states or oxidation numbers that you have to come up with, and so that's why you want to be pretty quick and proficient at it. And in a second, we're going to be balancing redox reactions, which is a little bit different because we've got to pay attention to the balancing not just atoms, but also balancing charge and electrons. And so you're really going to want to be able to figure out oxidation numbers pretty quickly. Okay. All right. So our example here. Identify which compound was reduced, oxidized, okay, and which is the reducing agent. Okay, if you know these things, then this is should be trivial. Okay, what's the reducing agent? What's the oxidizing agent? Okay. All right, so we have sulfuric acid. Okay, reacting with hydrobromic acid, HBr. Just giving you SO2. Elemental bromine. Oops. Elemental bromine is diatomic. Okay, and then water. All right. So let's figure out our oxidation numbers for all these guys. All right. Well, for this guy, it's -2, so that's -8. These are going to be, that's going to be each one of those +1, so +2. And so the sulfur is +6, right? Yes. Okay. And then this again is going to be +1. This is -1. Okay. Here, oxygen again, -2, going to -4. So this is +4. And you already notice that sulfur is changing its oxidation number. Okay, it is becoming less positive. So, so you had to add electrons to bring that number from +6 down to +4. So this was reduced. Okay. All right. So now, what was the reducing agent? Reducing agent. Well, this is bromine in its elemental state, right? So that is a 0 oxidation number. Okay. So bromide gave up electrons. Bromide was actually the reducing agent that reduced sulfur. Okay. And then in water, this was -2. This was, each one of them was +1, +2. Okay. So the things that changed are sulfur changed and bromine changed. Okay. So let's see. Bromine was oxidized. And is the reducing agent. Okay. And then sulfur was reduced. Okay, went from a more positive number to a less positive oxidation number, and is the oxidizing agent. Okay. All right. Okay, another example for you. Just make sure we're good on this. Okay, and this is I'll just say identify same things. Okay, same instructions as that. Okay. For copper sulfate plus zinc metal goes to copper solid plus zinc sulfate. Okay. Go through, do all the oxidation numbers. All right. Each one of those is -2, so that's -8. Okay. Copper is going. Yeah, here might be helpful. This might be hard if you don't have in your memory bank that sulfate is a -2 ion, -2 polyatomic ion. So if this is -2, that has to be +2. Okay. So +2. All right, which means the sulfur is +6. Oxidation number. All right. This is zinc in its elemental form, so that's 0. Okay. Copper in its elemental form, so that's 0. All right, and then here, -8. And again, this is, this is, what do you call it? +2. Okay, and this is just like it was in the other column, +6. So in this reaction, sulfur doesn't change, but obviously zinc and copper change. Okay, so zinc gave up electrons. Okay, so I'll do it a little bit kind of opposite order from how I set it up there. Zinc. Oh no, I guess that's exactly the same order. Zinc was oxidized. Okay, lost electrons, and thus was the reducing agent. Okay, and then copper was reduced, okay, and is the oxidizing agent. Okay. All right, we got one more of these. Just hopefully drive it home. Clear my board for it just real quick. Next thing we're going to do is like I mentioned, the balancing of redox reactions, and that can seem a little bit complicated, but there's sort of a recipe for how you do it, and if you know the recipe, the individual steps of that recipe aren't that bad. You just have to be sort of careful along the way. But you want to be good on this stuff, on figuring out oxidation states and what was reduced and what was oxidized. So we'll do this last example here. All right, so directions this time are for the reaction below, identify oxidation number of all elements, like we've done here. Okay. And state the total number of electrons transferred. That shouldn't be too hard. Okay. We're just going to have to see, you know, how oxidation numbers changed. Okay. If the oxidation number changed, you know, 2 units, it went from a +2 to a 0, then you know the 2 electrons were transferred. Okay, but then you also need to keep into account, well, okay, that happened, that's what happened to each +2 cation. How many of those ions were there? Oh, there were 3 of them, so that would be 6 electrons transferred. Okay, all right. Oh shoot, this guy's got a bag on me. So sorry, let me erase this guy real quick. Okay. All right, so, yeah. Okay, and here's an example, one of the rare situations where oxygen is not -2, okay? I said be on the lookout for hydrogen peroxide. H2O2 is hydrogen peroxide. Plus CO7 gas plus 2 hydroxide goes to 2 hydrochlorine. Waters, 4O2 gas. Okay. All right, so let's go through and do these oxidation numbers. All right, so in this situation, I mean, it's overall neutral. You know that the hydrogens, they're attached to a non-metal, so the hydrogens are going to be +1 each, right? So +1. Overall, because there's 2 and +2. And so each of these actually, in hydrogen peroxide oxygen, each oxygen is -1. Right, so -1 over an overall -2. Okay. Now in this compound here, oxygen is -2 for a total of -14, which means each chlorine has to add up to an overall of 14, so each one is +7. Okay. Oops. This guy is hydroxide. Okay. So our oxygen, as is usually the case, is -2, -2. This is +1. All right. Here, -2. There's 2 of them, so it's -4. Now, this is polyatomic ion where the overall charge is -1. Okay, so if the sum of the oxidation numbers for oxygen is -4, then this must be +3. Okay, that way when you add them up, you get the overall charge of the polyatomic ion. Okay, water, it's -2 +2, each hydrogen is +1, and oxygen, in its elemental state, it's 0. Okay. All right, so okay, so what got oxidized and what got reduced? If we look here, we see that the chlorine changed its oxidation number. It became less positive. Okay, so it accepted electrons. Okay, so it was the oxidizing agent, and it got reduced. It went from +7 to +3. All right, and the reducing agent in this situation, pretty unusual because hydrogen peroxide is often an oxidizing agent. But in this situation, it was a reducing agent, and the oxygens went from -1 over here to 0. Okay. So let's look at how many electrons were, okay, so that was the reducing agent. Okay. This was the oxidizing agent. Okay. So each one of these gave up 1 electron, right? And so there's, oh, I'm sorry, gave up 2 electrons. There's O2, each one is -1, and so the pair of them gave up 2 electrons times 4, 4 hydrogen peroxide molecules. So there are 8 electrons transferred. Okay. 8 oxygens gave up 1 electron each. Okay. And then 2 chlorines. Okay, there were 2 chlorines here, and each chlorine accepted 4. Okay, you want to make sure these match up. Okay, number of electrons accepted equals the number of electrons given up. All right, so now we're going to move on to the long-awaited balancing redox reactions. Okay. So you're going to be given an overall reaction that is not balanced. Okay. It's a redox reaction, and you're going to need to pay attention not only to the number of atoms to make sure, as we've done in the past, that the atoms are the same, but the number of electrons transferred are the same. Okay? And so you're going to get an overall reaction. You're going to want to be able to identify what got oxidized and what got reduced. That's why we do it on these practice ones. Okay? And you're going to break it up into what's called half reactions. Okay? You're just going to take the, let's say it was copper 2 plus going to copper metal. Okay? So that would be the half reaction for the reduction process. Copper 2 plus going to copper metal, that's a reduction process. Then you want to break it up in the half reaction for what was the oxidation half reaction. Okay? And then you're going to sort of balance each of those half reactions. And once they're balanced, you're going to add them back together. Okay? That's sort of the general principle. Specifically, when you're balancing the half reactions, the first thing that you're going to want to do is you're going to want to do sort of the old-fashioned, pardon me, are there any atoms that, in this half reaction, are there any atoms that, have an unequal amount, on the reagent side versus the product side? Is there any atom where, oh, there's 2 over here, 1 over here, so we have to balance that part, okay? So you're first going to do that, and you're going to do that first without oxygen and hydrogen. You do those separately. So you look at all the other atoms that might be in there that aren't oxygen or hydrogen, and you're going to balance that, okay? So step 1 is going to be break it into your half reactions, okay? And obviously we'll do examples. You break it into your half reactions. Step 2A is going to be, balance any atoms that aren't hydrogen and oxygen. Okay. Step 2B, then we're going to deal with imbalances in oxygens and hydrogen, which is fairly common in these. And the way you handle that, actually, is if there's an imbalance in oxygen, you're going to add enough waters. Okay, each water has one oxygen atom. You're going to add enough waters on whichever side needs it so that the oxygens are fixed. Okay. When you do that, that will throw off your hydrogens. Okay, now because you've added a water, every water molecule brings along 2 hydrogens. That will throw off the hydrogens. That's okay. Whichever side now has more hydrogens, you're going to put a proton, an H+, on the opposite side to balance out the hydrogens. Okay, and then once you're done, so that's 2. That's 2C when you're balancing out the hydrogens. Figure out 2C. Yeah, and then you're going to want to make sure that the number of electrons transferred is correct. Okay, by looking at changes in oxidation numbers, okay? So if you see that going from starting material to products, that 2 electrons were given up, okay, you're actually going to write 2 electrons on the product side, okay? Or maybe 2 electrons were accepted, so you'll write 2 electrons on the reagent side, okay? And so then that half reaction, and you'll do it to both half reactions, those half reactions will be balanced, okay, independently. But now we need to combine them back into the overall reaction. And the first thing we'll do for that is to make sure that the number of electrons given up equals the number of electrons accepted, okay? Or maybe it was this way, maybe it was the accepting on here. And I know this is a little bit hard with me just waving my hands, but we're going to do examples. They may not be the same in one of those half reactions. And so, you know, let's say this one had only 1 electron transferred, but this one had 2 electron transferred. So you would multiply this entire half reaction. You put a 2, multiply it by 2, so the number of electrons transferred equal to each other before you put them together. Okay, so all the coefficients of the starting materials and the products in this half reaction, you can multiply by 2. Once the number of electrons transferred equals each other, now you can stack them and you can add them together, adding everything on the reagent side to make the overall reaction, adding everything on the product side to make the overall reaction. But anything that's the same on both the product, let's say you got 2 waters over on the reagent side, you got 2 waters created in the overall process, they can cancel out. Okay? And the electrons will obviously cancel out because we made sure that it was the same number of electrons, so those will go into the overall reaction. Okay? That's simple enough. Got it? Do we even need to do an example? Yeah, okay, yeah, probably. Okay, folks, so let me go ahead and write down that process and stuff and put it into words that I just tried to describe to you verbally, and then we'll do some problems with it. Yeah, okay, so I'm hoping I have the outline correct, that this is section 2. All right. Balancing redox equations. Okay. Learned balancing in chapter 3. Okay. Same number of atoms on each side of an equation. Okay. With redox reactions, must also balance number of electrons exchanged. Okay. All right. Now we're going to learn that there are you can break the conditions into 2 separate categories. Balancing a redox reaction in an acidic media or in a basic media. What I described to you before was basically how you do it in the acidic media. And then the basic media is actually the same procedure, but with just, depending how you look at it, 1 or 2 steps added on to the end. So you really learn the acidic one, and then once you've got that down good, then you're most of the way there for doing the basic media. You just have to recognize those 2 extra steps. Okay. Pardon me. All right, so this first one is balancing an acidic media. acidic solutions. Okay. Yeah. So is that the? Oh. Sorry. So sorry. Oh, sorry. Okay, there it is. Yeah. So yeah, you could have. Just want to show you an example of an unbalanced reaction, a redox reaction called the skeleton reaction. All right, so pure copper mixed with nitrate. A lot of these don't have the counterions. If your skeleton reaction doesn't have the counterions, then you don't have to worry about it. So, you know, whatever cation went along with that, so forth and so on. Copper 2 plus. And plus nitrite. Okay. All right. Okay, so here's the process that I tried to describe to you earlier. And it's important that you, you know, really take a good look at this process once we get it written down. And you keep track of the numbers, like step 2A, step 2B. Because when we do an example, I'll say, okay, this was because we were doing step 2B, or whatever the case may be. All right, so process. Okay, 1. Separate the oxidation half reaction and the reduction half reaction. Okay. We can tell right here, for instance, that copper going to copper 2 plus, that is going to be the oxidation half reaction. And then nitrate going to nitrite, nitrogen dioxide is going to be the reduction process. We know this is the oxidation process because this is losing electrons to form that. Okay. All right, and then we'll separate both reactions and we'll sort of deal with them separately, and then we bring them back together. So step 2. Balance each half reaction. Okay, and you want to do these steps in order. Don't mix up the order. Okay. All right. So step A. Balance elements other than hydrogen and oxygen. Okay. You know, if your half reaction had you know, 2 chromiums on one side and 1 chromium on the other, you would need to balance that part. And now we'll deal with oxygen and then hydrogen. Okay. Let me underline other. All right, and then balance oxygen by adding H2O. Okay? So if you've got more oxygens on one side of the half reaction than the other, you're going to add water on the one that has the fewer until you've got enough oxygens to balance that. Okay? And then this will likely create an imbalance in the number of hydrogens, because water also brings along 2 hydrogens. And so you're going to balance that, balance hydrogen by adding H plus to whatever side is needed. Okay? All right, and then for 2C, right? No, 2D. Where am I going to put that? D. Okay. Balance charge. Okay. The charge on both sides of the half reaction has to be the same. So if it's neutral on one side, it's got to be neutral on the other. If it's +1 on one side, it's got to be +1 on the other side. Okay. So you're going to balance the charge on both sides. By adding electrons. Okay? All right. Once you've gotten to that point, you will have successfully balanced the half reactions, and now you're ready to bring them together. However, you need to make sure that one of the half reactions is going to give up electrons, and one of the half reactions, by definition, oxidation half reaction, reduction half reaction, the other one will consume electrons. You have to make sure that the number of electrons consumed is the same as the number of electrons given up. Okay? And so you can do that by multiplying the entire balanced equation, the entire balanced half equation, by whatever integer you need to do it. If one of them consumes 2 electrons, if the reduction half reaction consumes 2 electrons, and the oxidation creates 1 electron, then the oxidation half reaction has to be multiplied by 2 so that they equal. Okay? Again, this will also, once we do an example, this will seem a lot more clear. All right. Okay, and so in order to do that, that's going to be step 3, we'll call that. Multiply each. You may have to multiply both of them by an integer. You may only need to multiply one of them. Multiply each half reaction by integer, so that electrons exchanged match. Okay? You now can add the 2 half reactions. You're going to sort of line them up right over each other. All the things on the reagent side, all the things on the product side for both equations. Okay, and you're just going to add them, except anything that appears on one side of one of the reactions, but is also on the other side. Say it's on the reagent side on one of the half reactions, and the exact same thing is on the product side, then those cancel out. Okay, those didn't take place in the reaction. It didn't have a part in the reaction. All right. Now add half reactions. Okay. By canceling compounds. And you might be canceling an entire compound, let's say, what's a good example? It's often water is one of them. So, maybe you've got 2 waters on the reagent side over here, but on the other half reaction, you've got 2 waters created those will cancel out and they won't be in the overall balanced redox equation. Okay? But sometimes it'll just be a matter of, yes, you've got the same compound, but you might have different numbers. So you might have 2 waters over here and 3 waters over here. That means you can cancel out these 2 waters and all but one of these waters. One of the waters has to stay. Okay? And we'll see that in our examples. Okay? All right. And then it good to do a double check. That atoms are balanced, you know, like the old-fashioned, just looking at the atoms, making sure same on reagent side and product side, and your charges too. The charges need to be the same on both sides. Are balanced. Okay, that's the process. All right. Yeah, we're first, before we balance an entire skeleton redox reaction, we're going to just try balance it. We've got a half reaction here, and we're going to try balancing that so that you get an idea of doing this process up to 2C. Or I'm sorry, up to 2D, that we can do it for a half reaction. Okay. Clear up some board here real quick. Okay. All right, so let's do an example of balancing a half reaction. So this is B. Reaction only, and again, important to note that it's in acidic media, or acidic solution, common way to say it. Okay. So just 2A to 2D. Okay. Step 1 was dividing them into the half reactions. Okay, so example. Complete. And balance the half reaction in acidic media. Okay. All right, so we have ClO3 minus. Okay. 2Cl minus. Okay. All right. So 2A is balancing any non-oxygen or non-oxygen or hydrogen element. Okay. Not needed here because we have one chlorine, so no need. The only thing we do have to deal with the oxygens. Okay. All right. So here we can, let's see, how do I want to show it? All right, I'm just going to put in parentheses here. 2A not needed. Okay. All right, so what we now need to do is we need to balance the oxygens by adding water. So we'll add waters to this side because that one has 3 oxygens, there's no oxygens over here. Okay, so ClO3 minus, okay, Cl minus, aqueous, plus 3 waters, okay, liquid, all right, and yeah, I meant to do this in red, but that's okay. So this was step 2B, okay. All right, so now we're going to do 2C. We've now put a bunch of hydrogens on this side, but there's none on that side, so we'll add protons to that side. Okay. ClO3 minus. Sorry, just color coding here. Apologize for obsessiveness. All right, we need to add 6 protons because that's how many H's we have over there. Aqueous. All right, and this is step 2C. Okay. This is Cl minus, aqueous, plus 3H2O. Okay? All right, now our oxygens are balanced, our hydrogens are balanced. Now we need to balance charge. So on this side, the overall charge of the reaction is neutral, but on this side, it is -1, okay? So we're gonna need to add 1 electron. The only way we have to adjust the charge is to add electrons, and so the only way we can fix this imbalance in charge is by adding an electron to this side. Okay, so electron plus six protons, ClO3 minus, L minus 3H2O liquid. Okay. Oh, I'm so sorry. Terribly sorry. So, yeah, there are 6 protons there. So overall, this is +5. And this is -1, so sorry. What I actually need to do is add 6 electrons, right? And just ignore that 6 coefficient there. Right there. Okay, and this was step 2D. Sorry about that. Okay, so we have six positive charges here, and the 1 minus is an overall +5, and we have a minus here. So now the electrons sort of neutralize the protons, and we have a -1 there, -1 there, so it's balanced by charge. Okay? So that's how we do balance a half reaction. Okay? So now let's try that with a skeleton reaction, break it into 2 half reactions, and balance the whole thing. Very exciting. Okay. Okay, so the next one. It's going to be C. Oh. Yeah. C. Examples of balancing a complete, not just a half, reaction in acidic solution. Okay. All right. Need to make sure I have plenty of space for this. Okay, I'm actually write that down. I'm gonna erase that. This guy uses up a lot of board here for this. Okay, so our skeleton reaction is copper solid. Okay, so pure copper plus nitrate. Right. Goes to copper 2 plus NO2. Okay, this is the one that we showed at the beginning. Now we're actually going to go through the process of, oh shoot, that's a G, gas, of balancing. Okay. All right, so we have our two half reactions. Copper going to, as I mentioned, copper going to copper 2 plus. So our oxidation half reaction. All right, so step 1. Okay. I'm gonna, yeah. All right, so. And then nitrate to nitrogen dioxide. Oh yeah, actually that would have been a good first step to think about what are the oxidation numbers here. So that's 0, -2, so that's -6. It's overall negative, so you know that this is +5, right? Okay. And then this is +2, right? +2, so -4, so +4. Okay. So nitrogen is getting reduced. It's going from N +5 to N +4. Okay. All right. So let's deal with that half reaction first. All right, so we have NO3 minus aqueous going to nitrogen dioxide gas. Okay, that's one half reaction. All right. We have, there's no need to do step 2A because the only other element besides oxygen and hydrogen is nitrogen, and the nitrogens are balanced, one on each side. Okay, so no need. Step 2A. All right. But we do need to balance the oxygens, right? We have 3 oxygens here, but only 2 oxygens there. So we'll add, to this side, we'll add a water molecule. Okay, it's going to be step 2B. Gas. This is NO3 minus aqueous. Okay. Now we need to balance the hydrogens. So we're going to add 2 protons on that side. Okay. And that is step 2C. All right. Go. I meant to show that as a whole new, I don't know if that's helpful for you guys or not. Probably not needed, but anyway, that's the way I have it in my notes. All right, so doing the next step, we come down here again. It's going to be 2 protons. Plus NO3 minus going to nitrogen dioxide plus H2O liquid. Okay. I didn't need to erase that. That's step 2C. Okay. All right. Now we need to balance the charges. Okay. So on this side we have 2 pluses and 1 minus, so an overall of +1. Over on this side it's neutral, so we're going to need to add an electron to that side. Okay, so this arrow a little shorter. Okay, so an electron plus 2H plus nitrate goes to nitrogen dioxide. H2O liquid. Now that half reaction is balanced. Okay. Let's match my notes. Indeed it does. Okay, so perfect. Now we can deal with the other half reaction. Okay. I'm going to partition this guy here. Okay. And our other half reaction is copper solid turning into copper 2 plus. Okay. And there's going to be no need to do 2A, B, or C because all the atoms are balanced. We only have 2 atoms. We have 1 copper atom on one side, 1 copper atom on the other, and they are balanced. No oxygens to worry about, or hydrogens, so forth and so on. Okay. So no need 2A, B, or C. All right. We do need to balance charge. Okay, so we've got 2 plus here, neutral over there, so we'll add 2 electrons here. Copper 2 plus. Okay. Copper solid. Okay. And of course, again, just to remind you, that's step 2D. All right. Okay, perfect. So we are now almost ready to add the 2 half reactions together. Okay, except we need the number of electrons consumed on the reagent side, in this case, to equal the electrons produced on the product side. Okay, and so we have 2 produced here, but only 1 consumed here. So what we're going to do is we will take this entire thing and we will multiply it by 2. This is step 3. Okay, so that's going to end up, I'll do something wacky here. You'll see why I'm doing it. As you know, I get a little obsessed with these color coding sometimes. All right, so we have electron. I'm not going to write in the coefficients yet. H plus aqueous plus NO3. I'll write in the coefficients in a sec. I know you're like, what is he doing? Okay, goes to nitrogen dioxide, gas plus H2O. Okay. Now, fancy. That's going to be 2. That's going to be 4. That's 2. That's 2. And that's 2. Okay. Yeah, perfect. Okay. So now we can actually add these two half reactions. I'm going to do that in this space right here. Okay. Yeah. I'm going to rewrite these just so they line up nicely. I'm just trying to be, super clear. So pardon me if you're like, why is he bothering to rewrite those darn things? All right, so we have copper solid going to copper 2 plus aqueous plus 2 electron, okay? And then we're going to add that to this half reaction, 2 electron plus 4H plus aqueous plus 2 nitrates. To 2 nitrogen dioxides plus 2 H2O liquid. Did I do that correctly? Yes. Okay. Yeah, and so sometimes there's other things that cancel out, but in this situation, the only things that cancel out, the only things that are on the product of one side and the reagent of the other are the electrons. Okay, and that was by design. Those are always going to cancel out because we wouldn't be doing this adding step if they didn't. All right, so we'll just say that is what was that step? What about step 4? Yeah. All right. So. Step 4. And now we can put the whole thing together. So 4 H plus. The order in which you put these reagent, it absolutely doesn't matter. Okay. Plus 2NO3 aqueous plus copper solid goes to copper 2 plus aqueous plus nitrogen dioxide gas plus 2H2O liquid. Big one. Here's our final balanced redox equation in acidic solution. Okay. All right, so now we're going to do balancing in basic solutions. Okay. And all we're going to do in the basic situations is we're basically going to get to this point, and then we will, we know that having H plus, having strong acid like that around in a basic environment doesn't make any sense. Okay. So what we're going to do is we're going to add, you can always do, one thing you do to one side of the equation, you do the other, and you haven't changed it. So we're going to add enough hydroxides to get rid of the H pluses, okay? And we'll do it on both sides. So we'll add, if we were doing this one, say, in basic solutions, we would now add 4 hydroxides on that side, 4 hydroxides on that side. Okay, the 4 hydroxides and 4 H pluses would turn into 4 water molecules, okay? And some of the water molecules would cancel each other out, right? Because we have water over on this side and water over on that side. So we would end up with 4 waters here, 2 waters here. We'd get rid of all those waters and 2 of those waters, okay? And you'd be left with also those 4 hydroxides. Nothing would happen to those 4 hydroxides. Okay, make sense? Okay, perfect. And actually, I think I explained that Yeah. You don't typically, yeah, you don't get to this stage. You do the hydroxide part on each half reaction before you bring it together. Sorry, I said that muddled. Okay, so let's take a look at one. Oh. You can see where knowing how to figure out oxidation states and oxidation numbers, knowing how to figure those things out, same thing. Knowing how to do that pretty fluidly is really important because these problems are kind of involved. Okay. All right, so this is D. Balanced redox reactions in basic solutions. Okay. Oops. Can do with a trick, so to speak. Okay. Do exact same process as with acidic solutions, but add a step. Okay. All right, step 2E. Because the solution is basic, okay, add hydroxide, sorry, very strong base, add hydroxide, both sides of a half reaction to quote unquote deal with, really it's neutralize, you could say, to deal with the H plus added. Okay. This creates some H2O. Cancel as appropriate. When adding the half reactions. Okay. All right, so let's look at an example. Erase this guy. Sorry. I guess you can always pause it in a normal class. I don't like to write it and then erase it immediately, but you can always pause it. Okay. Okay. Like we did with acidic media, where we only did one half reaction doing this technique, we're going to do that. We're going to do it on a half reaction in basic solution, and then we'll do an overall skeleton of an entire redox process. Okay, just like we did before. All right. So E. Example. Balancing half reaction in basic media. Or basic solution. Sorry, I keep saying basic media. Okay. I always get these from problems that I find in the book someplace. And so the exact instructions that it says are complete and balance. The half reaction, basic solution, but it's just exactly what I say up there. Sorry, that's redundant. And is the half reaction a reduction or an oxidation? All right, so we can fit this in here. All right, so we've got manganese 2 plus. Okay, going to manganese dioxide. All right. Let's first make sure of our oxidation states, just so that this is obviously +2. Okay, that's going to be -4, so this is +4. Okay, so already you can tell what it is, that this is an oxidation process. Yeah, the manganese 2 plus is losing 2 more electrons to become manganese +4. Okay. All right. So now 2A is to balance any non-oxygen or hydrogen atoms, and as happens a bunch of times already, we no need to do 2A. No need. Step 2A. Okay, because we don't have any, the only other element is manganese, and we have 1 on each side. Okay, so the next thing to do is to balance the oxygens. We've got 2 over here, so we need to add 2 waters over there. All right, so 2H2O plus Mn2 plus. And obviously, when you're doing these problems, you don't necessarily have to do the, I do one step, rewrite the equation. Another step, rewrite the equation. Maybe a safe way to do it to make sure you don't make any mistakes, but if you want to, you could add, I just did 2B, you could add 2C, make 2C part of this and add the protons over here. Okay, so manganese dioxide, solid, that's step 2B. Okay. All right, and then we will add, since we added 4 H's over there, we got to add 4 protons here. Okay. Oops, liquid. Okay. Step 2C. All right. And now step 2D is we've got to balance our charges, right? So we have 2 plus on this side, we have 4 plus on this side. All right, so we'll add 2 electrons over here so that it's 2 plus and 2 plus. Okay. Okay. That was step 2D. Okay. All right, so we're now, this would be the balanced half equation if we were in acidic media, but we're not in acidic media, so we got to deal with these guys here. So what we'll do is we'll add 4 hydroxides to either side. That'll take care of the H pluses. Okay, so. Like I said, I'm really drawing this out each step. You could combine those already and just create the waters, but I want you to be able to look back at your notes and see, oh, wait a second, how did we get there? Okay. Okay. Oh, and then our 2 hydroxides on this side as well. Am I doing this correctly? Nope. I am not. Oh, 4 hydroxides. Right. Right. Okay. 4 hydroxides. Okay. And that was step 2E, that added 1 for basic solutions. All right, so now what that means is you now have 4 H2O liquids, 4 protons and 4 hydroxides makes 4 water molecules. Okay. Still got your 2 electrons, your manganese dioxide, okay. Manganese 2 plus, our 2 waters here, and we'll cancel those out in a second. All right, and our 4 hydroxides. Okay. Really drawing this out. Again, you could probably combine some of these steps, but do so carefully, okay? And a lot of times when we take shortcuts and try to take too many shortcuts, we make careless mistakes, okay? So we've got 2 waters over here and 4 waters over here. We can cancel at least 2 of them. All right, so those go away, and then this will change to 2, okay? And so the final balanced half equation, basic solution, is 4 hydroxide plus manganese 2 plus manganese dioxide solid plus 2 electron plus 2 waters now. Okay. All right, did I get the correct answer? I did. Great. Okay. All right. Let's do an overall skeleton. Balance skeleton redox reaction in basic solution. Okay, this is sort of our grand finale for these balancing situations of redox reactions. Anyway. example of balancing, completing and balancing, I always like to say. A complete, not a half, reaction in basic solution. Okay. All right. I won't write the example, the instructions, because the instructions are almost exactly my heading right there. Okay. All right. This is kind of a beast. Hopefully I can fit it all in. I'm gonna erase that guy again, so that I make sure I have as much board as possible. All right. We have chromium hydroxide. Okay. Plus hydrochlorite. Okay. Chromium tetroxide. Okay. Aqueous. Plus chlorine gas. Okay. First thing we should do is do all our oxidation numbers. Okay. So we know that each hydroxide is a -1 polyatomic ion. So we know that this chromium, since it's overall neutral, is +3. Okay. And yeah, these are negative. Yeah. So that's -2 and -6. That's +3. So overall neutral. Okay. This guy is -2. Since it's an overall -1, this guy is +1. Okay, that's the only way you could have an overall charge of -1 for the hypochlorite. Right here, we know that each is -2. -8. Since the overall charge is -2, that must mean that this guy is +6. Okay. All right, so that we see that the chromium is losing electrons, so our oxidation half reaction is going to be this to that, okay? And then our chlorine, so chlorine gas, what's the oxidation state number of that? Well, that's in its elemental form, it's 0, okay? All right, so we can split these into their half reactions. All right, so we're going to have chromium hydroxide. Okay. And that's going to 0.4. Chromate. Okay. Aqueous. Okay. And then our other half, well, let's do one at a time. That helps our space on the board a little bit better that way. Okay. All right, so our first step is going to be to, let's see. Nope. Again, no need for 2A. I thought I could have sworn we had an example where you needed to do 2A. But I guess we haven't had a single example. Again, be prepared if you ran into one of those problems like, let's say, we had one chromium over here, but 2 chromiums over here, you'd have to put a 2 coefficient in front of that chromium there, okay, to balance out the chromium. Okay, but we don't, the only things that are out of balance are the oxygens and hydrogens and stuff, so we'll deal with those. All right, so, and again, do it in order, so we're going to deal with the oxygens first. We've got 3 oxygens on that side. We've got 4 oxygens on this side. So we need to add a water molecule on this side. right, so just one. All right. All right. Now we need to balance out our H's, our hydrogens. Okay, so, oh, I guess actually, yeah. Okay, in my notes, and I think I'll follow by this, I did combine some steps. Okay, so let's go ahead so that we don't draw this thing out too much, because we do got to do that hydroxide stuff eventually. All right, so we now have we have 5 H's on this side, so we got to add 5 protons on this side. Okay. And then now we need to balance our charge. So our charge over here is -1. Our charge over here is neutral. Okay, so we need to, little mistake here. What is my mistake? I'm sure you've all realized it by now. We got to add 5 protons on this side, not just 1 proton on that side. Sorry, I'm tired here. Because we have 5 H's on this side, so plus 5 H plus. Okay, now let's look at our charges. Our charges over here is +3. It's neutral over there. Okay, so we need to add 3 electrons. Okay. All right, and we can. So this is. I don't know if this is helpful or not. That's step 2B. This is step 2C, and this is step 2D. Okay. All right, perfect. So this is now a balanced half reaction, but it's a balanced half reaction. How it would look in an acidic solution, we need to do it how it would look in a basic solution. All right, so because of the 5 H pluses, we'll add 5 hydroxides. Okay, so plus 5 hydroxide. All right, and we've got all our other stuff in this equation. Our 3 electrons, okay, and our 5 H pluses. Okay, and our chromate. Okay, oops. Chromium hydroxide and our water. Make sure there's no mistake. There is no mistake. Okay, perfect. We are now going to get, let's see. Yeah, I guess I'm showing this again. All right. These guys are going to combine. I'm going to shorten this. Those are going to combine, and those are going to give us 5 H2Os, right? Okay, we've got 1 H2O over there. Okay, so we can end up canceling out one of those H2Os, canceling out that H2O. All right, so that what we now have is, oh, shoot. I'm so sorry, folks. I forgot to add the 5-hydroxide here. When you add the hydroxide, you got to add it to both sides. All right. So we've got our, now it looks like 5-hydroxide. Okay. Chromium hydroxide. Okay. Going to chromate. electron plus 4 waters. Okay. Perfect. Okay, great. All right, so now let's do the other half reaction. We'll sort of segregate space here. All right. And this is hypochlorite to chlorine. Here's where we have to balance, where we do need to do step A. Okay, right, our chlorines aren't balanced. All right, so we're going to make that a 2 there, and that's step 2A. Finally, we got to do it, yay. Okay, now we've got to balance our waters. All right, and so we'll add, we have 1 water over there. Let's see, sorry. Oh, no, I'm sorry. We have 2 oxygens over here, so we're going to add 2 waters over here. Okay. Up. Okay. And because of that, now we have 4 H's over here. We've got to add 4 H's over here. All right, or 4 protons, sorry. 4 protons, so sorry. I'm winding down here. 4 protons. Okay. We've got our 2 hypochlorites. All right, now let's check our charges here. We have an overall, so +4, +2, so, or -2. So we have an overall +2 charge on this side, overall neutral here. So we got to add 2 electrons so that we have this side end up neutral as well. Okay, so 2 electron. So sorry. I was going to make these red. I like, anytime I do a new thing, make it red, like I did here, but oh well. So this was, that's 2C. This is 2B in terms of steps, yeah, and this was 2C. Okay, all right, great. So, but now we got to add hydroxide, 4 hydroxides to both sides because we got to deal with the H+ that can't exist in a basic media. So, 4 hydroxides, okay, plus 4, oh, try to stick with my color coding. There we go, it's helpful. 4H+, okay, plus 2 hypochlorites, okay, chlorine gas, right, plus 2H2O liquid, plus 4 hydroxide. Sometimes hydroxide is represented like that, sometimes it's represented like that. Doesn't really matter. Okay, so these guys are going to create 4H2O. Okay, we have 2 H2O here, So those guys are going to cancel out, and this will turn into 2. All right, so that we end up here with, what do we end up with? We're going to end up with, let me make sure I'm on the right track. I am. We're going to end up with 2H2O liquid plus 2 hypochlorites. Okay. And that goes to chlorine gas, okay, plus 4 hydroxides. Where do my electrons go? How did I lose my electrons? Ah, shoot. So sorry. Minus plus 2 electrons there, plus 2 electrons there. Okay? Right? Correct. Beautiful. Okay, so we are just about ready to add these guys together, except we find that here we are consuming 2 electrons, here we are producing 2 electrons. So we now need to balance the electron exchange, okay? So the way we're going to have to do that, let me see how I set this guy up. Okay. So what I'm going to do, so I'm going to have to multiply this whole thing, right, by times 3, right? That's going to make that 6, it's going to change all the coefficients of everything, but it's going to make that 6 electrons. And then I will multiply this whole thing by 2. Okay? Change all the coefficients, but make this 6 electrons. So we will have balanced the electron exchange. Okay? So what this guy is now going to look like is it's going to look like what? It's going to look like 6H2O liquid plus 6 hypochlorites. May I just double check? Yep. Plus 6 electrons goes to 3 chlorine gas plus 12 hydroxides. Okay, awesome. And then for this one, that's going to turn into 10 hydroxide, right? Okay, 2 chromium hydroxides, okay, going to 2 chromates, plus 6 electrons, yep, plus 8 waters. Okay, we're going to be able to do a bunch of canceling out here before we get our final beautiful answer. All right. Okay, so we're going to be, we've got water on this, 8 waters on that side, 6 waters on that side. We'll be able to get rid of all those, and this guy's going to turn into 2. Okay. Our electrons cancel out by design. All right, and then we're going to be able to get rid of some hydroxides as well, right? we've got 10 hydroxides there, 12 hydroxides there. We'll get rid of all those hydroxides. We'll get rid of all but 2 of those hydroxides, and we're done. And then we just write all the reagents, write all the products, and bada boom, bada bing. Okay, so what we should have is 6 Cl of hypochlorites okay, plus 2 chromium hydroxides okay, and that's going to go to 3 chlorine gas plus 2 chromates okay. We got rid of all but 2 of the hydroxides, so plus 2 hydroxides. Okay. And then we got rid of all but 2 of the waters, so plus 2 H2O liquid. Uh-huh. Uh-huh. Yeah. Mm-hmm. Mm-hmm. Correct. Easy, right? It's involved, but if you're very methodical, you know the steps of how you do it, which you're going to know from doing homework problems, then it's not too bad. Okay? Yeah, okay. On to the next step.